So today we're doing calculations involving the cubic unit cells. And let's review our units. All right, you've got to know your unit conversions. This is something we covered in my day one, also covered in high school and intro chem and all kinds of places. Make sure you remember your unit conversions. 10 to the 9th nanometers in a meter, 10 to the 10th angstroms in 1 meter, and 10 to the 12th picometers in 1 meter. Because when we're talking on the atomic level, we're going to be measuring things using centimeters or millimeters or kilometers. No, we're going to be using nanometers, angstroms, and picometers. So be able to make these conversions off the top of your head. Hopefully you still remember this from way back in the day. All right, there are 3 types of calculations we're going to learn today. 3 types. And I'm telling you right now, I'm going to pick one of these calculations and it'll be on the final. So one of these 3, you're guaranteed to see on the final. I can also ask all kinds of multiple guess questions about this kind of stuff because it's just easy. But I'm guaranteeing you, you're going to have to do one of these 3 kinds of calculations in the free response section of your final exam. So just word to the wise. So let's do this one together. The density of a crystal of thorium, that's a great name, huh? 7.84 grams per centimeter cubed, and it has a molar mass of 56.3 grams per mole. Now, if this wasn't a made-up element, how could you get its molar mass? Periodic table, right? So if this were, say, iron, right, you could get its molar mass from the periodic table. You're going to need the density. You're going to need the molar mass, because what are we doing here? We're using density to figure out which crystal type. So what are the 3 crystal types? Simple cubic, body-centered cubic, and face-centered cubic, right? So I would have to give you the density, and then you would need to look up the molar mass from the periodic table if it's a real element. If it's a made-up element, obviously I'd give it to you. If the edge length of a crystal of thorium is 0.279 nanometers, so I'd have to give you that. How many atoms are in each unit cell, which would then tell me which crystal type it is, right? Because if I get an answer of 1 here, which crystal type would that correspond to? Simple cubic. If I get an answer of 2, which one would that correspond to? Body-centered cubic. And if I get an answer of 4, that would correspond to face-centered cubic, right? So these are all posted in the notes online, so you don't have to write them all down right now unless you're just really looking to write really fast, right? You're going to list what you know. You're going to convert all your units to meters. Now, really, if you want to pick a different unit, you can pick a different unit, but they all need to be the same. It's easier if you get in the habit of converting everybody to meters based on what we'll be doing later on. But if you convert it to centimeters, that'd be fine too, so long as you're consistent. You're going to calculate the volume of 1 cell. Now, we learned this yesterday, or I should say on Monday. If this is a cube, what's the volume of a cube? Length times width times height, right? So that would just be edge length times edge length times edge length. Calculate the mass of 1 cell, calculate the mass of 1 atom, and then divide these 2 to get the number of atoms in 1 cell. So, oh, I forgot that I don't have a blank put in here. Now I'm going to go over this on the board so that we can really make sure we know where all our numbers are coming from. All right, so I've worked it out in advance, so I don't have to be standing here punching stuff on my calculator. So let's list. Okay, we know the edge length is 0.279 nanometers. And we know the molar mass, that was given, is 56.3, use your phone please, grams per mole. And we know the density that was given, 7.84 grams per milliliter, right? Now, just to refresh our memory, 1 milliliter is the same thing as 1 what? Cubic centimeter, yes? Okay, so let's go through our calculations. We want to convert everybody to meters. Or if you wanted to convert everybody to centimeters, that's fine, just be consistent, okay? So nanometers to meters, 0.279 nanometers. There are 10 to the 9th nanometers per meter. Right, that's one of the conversion factors we learned back at the beginning of the school year. So that would be 2.79 times 10 to the -8 meters, right? And then we've got our density in grams per milliliter. So that's the same thing as 7.84 grams per centimeter cubed, right? Because you need to remember back from the beginning of the school year, a milliliter and a cubic centimeter are the same thing. So 7.84 grams per centimeter cubed. How many centimeters are in a meter? How many centimeters are in a meter? Centi means 100. So if there are 100 centimeters in 1 meter, but this is centimeters cubed, so what do I have to do? I have to cube it, right? So this would be 7.84 times 100 cubed. So this would be 7.84 times 10 to the 6th grams per meter cubed. Now these guys are in the same unit, so I can do my multiplying, and they're not gonna be in any issue, right? Because when I multiply centimeters times meters, that's mess. We wanna keep these all in the same unit. All right, now we're gonna calculate the volume of a cell. Okay, if this is a cube, how do I get volume of the cube? A cubed, right? Because A, and A, they're all the same. So this would be A cubed. Which one of these is A? This one's A, right? So this would be 2.79 times 10 to the -8 meters. Now we're going to cube it. So when I do that, I get 2.172 times 10 to the -29 meters cubed. And I just punch it into my calculator and hit cubed. Now I'm going to get the mass of an atom, excuse me, mass of the cell. How can I get mass of the cell? Well, I know the volume of the cell, and I know the density of the cell. What's the formula for density? Density equals what over what? Mass over volume. So to get mass, how would I get mass? How would I rearrange this for M? Volume times density. So I've got volume. I was given density, right? Just solved for volume. I was given density. So volume of the cell times its density. So that's 2.172 times 10 to the -29 meters cubed. And here's its density. Notice that's why I converted it to meters cubed, so that these two, when I multiply them, meters cubed will cancel. 7.84 times 10 to the 6th grams per meter cubed. So that gives me a mass in grams. Let's see, I got 1.703 times 10 to the -22 grams. Is that a reasonable mass for the mass of a unit cell? Times 10 to the -22? Yeah, it is. Okay, now let's figure out the mass of an individual atom of this molecule. I mean, excuse me, of this metal. So, let's think about this. Avogadro's number is grams per mole, right? It's also grams per 6.022 times 10 to the 23rd atoms, right? That's what molar mass is, I should say. Not Avogadro's number. molar mass is grams per mole, right? And 1 mole is Avogadro's number. So if molar mass is equal to grams over Avogadro's number, then I can rearrange that because I know molar mass and I know Avogadro's number, right? So mass of an atom is molar mass over Avogadro's number. So the molar mass was given 56.3 grams per mole divided by 6.022 times 10 to the 23rd atoms per mole. Moles cancel, that gives me the mass of 1 atom. See how we were able to do that? So when I do that, I get 9.349 times 10 to the negative 23rd grams per atom. And this is grams per cell here. Is that a reasonable mass for an atom? Yes, that's a reasonable mass for an atom, right? 10 to the negative 23rd. So now all we need to do is figure out how many of these fit in one of these. And then that number will tell me the unit cell type, right? So we're just going to divide. Number of atoms per cell. We're just going to divide our two answers that we just got. Mass of the cell divided by the mass of the atom. So that's 1.703 times 10 to the negative 22nd grams per 9.349 times 10 to the negative 23rd grams. That comes out to be 1.8, which rounds to 2. So if there are 2 atoms in my cell, which cell type is this? This will be body-centered cubic, right? BCC. So there are several steps, but the good news is there's no stoichiometry, everybody's favorite, right? There's no balanced equation, everybody's favorite. There's no formulas to write. There's no redox. There's none of that. It's just basically manipulating the information that you're given. You ready to try one for yourself? I'll give you a few minutes to attempt this one. Iron. So it's a real element this time, not something made up. Iron has a density of 7.93 grams per milliliter, and its edge length is 0.286 nanometers. So I want to know, in each unit cell, how many iron atoms are present, and then based on that information, you can conclude which crystal type would you expect iron to have. I'll pause the recording. Let's try this one. All right, let's go over this one. So, what I recommend doing, beginning by listing all our information. Okay, so the problem, again, we're using density and molar mass to solve for cell type. So what does the problem give me? So given information or stuff that I could look up, right? The density is 7.93 grams per centimeter cubed, right? Because 1 milliliter and 1 centimeter cubed are the same thing. Also, we're given the edge length, A, which is 0.286 nanometers. And we know the molar mass. How do we know the molar mass? Is iron a real element? Yeah, we just look it up on the periodic table, right? Molar mass of 55.845 grams per mole. All right, so that's all of our givens. So let's go ahead and convert everybody to meters. Meters is a nice standard unit. So that if it's in grams per centimeter cubed, there are 100 centimeters in 1 meter, right? But this isn't converting centimeters to meters. This is converting centimeters cubed to meters, right? So I've got to cube my whole quantity here. So I'm multiplying 7.93 times 100 cubed, right? That's different than 7.93 times 100. So that gives me 7.93 times 10 to the 6th grams per meter cubed. And how many nanometers are in a meter? How many nanometers are in a meter? Nano sounds like what number? 9th, right. 10 to the 9th nanometers per meter. So that gives me 2.86 times 10 to the negative 10th meters. This is in grams per mole, so I don't need to do anything special there. It's just grams per mole. All right, so let's find the volume of a cell. And so how do I get V cell? A cubed, right. So I'll take my answer from here. 2.86 times 10 to the negative 10th meters, and I cube it. When I punch that into my calculator, I get 2.339 times 10 to the negative 29th meters cubed. Do we agree? Now, you might carry out a different number of decimal places, but you should still get something very similar. How do I get the mass of one cell? What information do I use to get the mass of the cell? Volume times density, right. So that's V cell times the density. So that's the number I just got. 2.339 times 10 to the negative 29 meters cubed. That's why I wanted to convert this to the same unit, right? So that when I multiply these two, meters cubed will go away and I'm left with grams. So 7.93 times 10 to the 6th grams per meter cubed. Meter cubed cancel, gives me my unit in grams. So I got 1.8548 times 10 to the negative 22nd grams. Is that a reasonable mass for a unit cell? Yes, that is reasonable. That's very, 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 very small. And then how would I get the mass of an individual atom? Remember, if molar mass is grams over Avogadro's number, then how can I rearrange this? I can say, therefore, grams is equal to molar mass over Avogadro's number, right? That's what I'm going to do. So, molar mass from the periodic table, 55.845 grams per mole, divided by 6.022 times 10 to the 23rd atoms per mole. Moles cancel. That gives me the mass of one atom. So I got 9.2735. And again, you might not carry out as many decimal places as I did. Times 10 to the negative 23rd grams per atom. And now, last step. How do I get number of atoms in a cell? All right, we're just seeing how many of these will fit into one of these, right? That's all we're doing. So this divided by this. So 1.8548 times 10 to the negative 22nd grams divided by this number we just obtained, 9.2735 times 10 to the negative 23rd grams. Gives me 1.99 is what I got, which is 2. So therefore, which kind of cell type is this? This would also be body-centered cubic. You feeling okay on how to do this? Now, the rest of the calculations we're going to learn are very similar to this. It's just kind of variations on a theme. It's a little bit wonky at first, right, because we're just not used to doing these kinds of problems. But I think once you do the practice, and we're going to do enrichment on it on Friday. So if you're feeling a little weirded out right now, we are doing enrichment on Friday. So worry not. Okay, now let's go the other direction. The first kind of problem we did, we used density to solve for crystal type, right? Now we're going to go the other way. I'm going to give you crystal type, and you're going to figure out density. Okay, so now we're going to flip-flop it. So here's the steps. I'm just going to start with the steps. I think that this one is a lot less involved, personally. I think it's a lot less work. So the first thing we're going to get is we're going to calculate M cell, which we already know how to do, right? Because if we can figure out the mass of an atom, which is just molar mass divided by Avogadro's number, and we can then convert mass of an atom to mass of a cell by multiplying by the number of atoms that are in the cell. Okay? So if we get mass of an atom and it's simple cubic, what will we multiply by to turn it into mass of the cell? It's simple cubic. What would I multiply by to go from here to here? 1, right? Because there's one net atom in simple cubic. If it's body-centered cubic, how would I convert mass of an atom to mass of a cell? If it's BCC, you'd multiply by 2. And if I have M atom and I'm converting it to M cell, what would I multiply for face-centered cubic? For 4, right? So you just need to remember 1, 2, or 4, right? Simple cubic, to go from here to here, you'd multiply by 1. Body-centered cubic, to go from here to here, you'd multiply by 2. And face-centered cubic, to go from here to here, you'd multiply by 4. Okay, so the math is not nasty, right? You're not taking natural logs or anything. It's all easy multiplying and dividing stuff. So you calculate the mass of the cell, and then you're going to calculate the volume of the cell, right? Because guess what? Density is mass over volume. So if you get mass of the cell, you get volume of the cell, you can find density. So if I do not give you edge length, maybe I give you radius. Could you turn radius into edge length? We did that on Monday, right? So if I don't give you edge length, if I give you radius, you could turn that into an edge length. And then you're going to convert it into centimeters. Why would you want to convert it into centimeters? It's a very specific reason why you want to convert it into centimeters. Grams per milliliter, right? Grams per centimeter cubed. That's why you want to convert this to centimeter. And then cube it, because centimeter cubed is milliliters, right? That's a volume. Once you've got the mass and the volume, you just divide them, and you've got the density. You're off to the races. Now you have to be told the cell type, right? You can't do this if I don't tell you the cell type. And you can look up the Avogadro, you can look up the molar mass in the periodic table if it's a real element. If it's something I just make up, then obviously I'd have to give you its molar mass. Does everyone understand the big picture on how we're doing this? Okay, like I said, it's not too nasty. I think once you get the hang of it and you do some practicing, you're not going to be as freaked out as your faces portray right now. So let's do this one. Nickel crystallizes as a simple cubic if the edge length is 0.3524 nanometers. What is the density of a crystal of nickel? Now again, I like to work these out on the board just so you can see where I'm getting all these numbers from. Let's see, did I work this one out already? I thought I did. Maybe I didn't. Let's see. Nope, I did not work this one out. Oh, maybe I've got it in the slides. Yes, I do. Okay. It's like, I know I worked this one out. Let's just do it on the board anyway. I'd rather you see it worked out. All right. So let's make that font a little bit smaller. Let's do 26. There we go. Oops. Review up. All right. I do have it in the slide, but I'd rather you see it written out. So this is nickel, right? Nickel, molar mass is what? It's 58.6934. Okay, and then I told you that it's simple cubic, and I told you that edge length is 0.3524 nanometers. And we're solving for density. All right, so the first thing we need to do is we need to find M cell. But before we can find mass of a cell, we need to find mass of an atom, right? And so M atom is what? We just learned how to do this in the previous type of problem. How do you get mass of an atom? Molar mass over Avogadro's number, right? So molar mass is 58.6934 grams per mole. Avogadro's number is 6.022 times 10 to the 23rd atoms per mole. So the mass of one atom, 58.6934 divided by 6.022 times 10 to the 23rd. That gives me 9.746 times 10 to the negative 23rd grams per atom. Now, this is simple cubic. So what do I need to multiply by? Right, we're multiplying by 1 since it's simple cubic. Right, so the mass of the cell is the same thing as the mass of the atom. So 9.746 times 10 to the negative 23rd grams. We'll leave grams per cell. But really it's just grams. Okay, now let's find volume of the cell. So how do I get V cell? We learned how to do this in the previous type of problem too. A cubed. But what does A need to be in? It needs to be in centimeters, right? So we take our edge length, 0.3524 nanometers. How many nanometers are in a meter? 10 to the 9th. That gives me meters. And then how many centimeters are in a meter? Times 100 centimeters per meter, right? So I got to do 2 calculations. So 0.3524 times 100 divided by 1E9, right? By the way, you can just multiply and use your exponents, right? That would move the decimal 2 over, and then that'd move it 9 back. But if you really want to put it in your calculator, you'll get the same answer. 1, 2, 3, 4, 5, 6, oops, lost track. 1, 2, 3, 4, 5, 6, 7, 8. 3.524 times 10 to the negative 8 centimeters. And now we want to cube that, right? Because we want A cubed. So that's A. A cubed would be 3.524 times 10 to the negative 8 centimeters cubed. Because centimeters cubed is a unit of volume. So when I cube that, I get 4.376 times 10 to the negative 23rd centimeters cubed. Now, if I wanted to go ahead and convert that to milliliters, that's the same thing. And now density is just what? Mass over volume. So this number, 9.746 times 10 to the negative 23rd grams, divided by my volume, 4.376 times 10 to the negative 23rd. milliliters. Milliliters, centimeters cubed are the same thing. So when you divide that, 4.376, you get an answer that's not on the massive exponent scale. Let's see, I can keep 4 sig figs. So 2.227 grams per mil. Is that a reasonable density? Yeah, that's reasonable density, right? You're not coming up with something times 10 to the negative 18th. That's a reasonable density. Do we see how to do this? Now here it is in the PowerPoint. Make sure I got the same thing that I got. Yep, I didn't carry out as many decimal places as I should have done. All right, you do this one with krypton. Krypton crystallizes as a face-centered cubic unit cell. It has an edge length of 559 picometers. I want to know what's the density of those unit cells. What's the density of krypton? Let's see what you came up with. Again, I'm going through these because I think seeing it and just slowing down and making sure everybody understands where every step's coming from is the easiest way to do these problems. I don't think they're inherently all that difficult. You just have to really watch what you're doing, right? Especially watch your units. And if you come out with an answer of density like 10 to the 6th grams per milliliter, you probably messed up one of your unit conversions somewhere. So what does the problem tell us? It tells us it's krypton, and we can look up its molar mass on the periodic table. That's 83.60 grams per mole. We're also told that it is face-centered cubic. And the edge length is 559 picometers, right? And we're solving for density. So density has the formula mass divided by volume, right? So the first thing we need to do is find M cell. But before we can do that, we need to find mass of an atom, right? So mass of an atom is molar mass over Avogadro's number. So molar mass, 83.60 grams per mole, divided by 6.022 times 10 to the 23rd atoms per mole. So I got for mass of an atom 1.388 times 10 to the negative 22nd grams. Now this is face-centered cubic. So what am I going to do? What am I going to multiply it by to convert mass of an atom to mass of a cell? It's face-centered cubic. So what am I going to multiply it by? 1, 2, or 4? 4, right? Because there are 4 net atoms in face-centered cubic. So when you multiply that by 4, I got 5.553 times 10 to the negative 22nd grams. So this is because it's FCC, right? That's why we're multiplying by 4. So 5.553 times 10 to the negative 22nd grams. Now we need to find B cell, and so that's A cubed, right? Let's figure out what A is. What unit do we want A to be in? It's currently in picometers. What do we want it to be in? We want it to be in centimeters because centimeters cubed is a unit of volume, right? So 559 picometers. How many picometers are in a meter? 10 to the 12. 10 to the 12 picometers per meter. And then how many centimeters are in a meter? 100 centimeters per meter. So when you do that conversion, I got 5.59 times 10 to the negative 8 centimeters. So when I cube that, 5.59 times 10 to the negative 8 centimeters. When I cube that value, I get 1.75 times 10 to the negative 22nd centimeters cubed. Do we agree? And now, density, we've got everything we need. Density is mass over volume. So we take our two answers, 5.553 times 10 to the negative 22nd grams, divided by my volume, 1.75 times 10 to the negative 22nd centimeters cubed. Centimeters cubed is the same thing as milliliters, so if you wanted to leave that as milliliters, you could. And we're keeping 3 sig figs, so I got 3.17 grams per mil, or 3.17 grams per centimeter cubed. Did you? Does everybody understand how to do these kinds of problems? It's literally the reverse of what we just did. All right. Let's look at, here's another one for you to try. I won't be able to give you as much time to do it though, just FYI, because we're starting to run low. But I'll at least be able to give you a few minutes to start working on it. You see a post online saying that calcium crystallizes as face-centered cubic with a radius of 197 picometers. But someone comments underneath it, no. The crystal is actually body-centered cubic. Now, because you're an astute chemistry student, you know that calcium has a density of 1.5 grams per milliliter. Who's correct? See if you can figure that one out. I'll pause the recording, and I'm not going to be able to give you as much time. All right, let's go through this one. Now, we are starting to run a little bit low on time, so I'm not going to handwrite out the solution here, but I think you'll be able to understand the method just by looking at a scan of my notes, which is what I put into the PowerPoint. So one person says that it's face-centered cubic, the other person says it's body-centered cubic, but the radius, that's not being contended, right? What's being contended is that whether or not it's body-centered cubic versus face-centered cubic. And you know it's density, right? So the method here is you're gonna have to do two calculations. You're gonna have to calculate the density assuming that it's face-centered cubic, right? Using the method we just learned. Then you're gonna calculate the density again, assuming that it's body-centered cubic. And then whichever answer is closer to 1.5, which is the known value, that's the correct answer. Does everyone see why you do two calculations here? Now watch this. Oh, I forgot it. I didn't turn this on. If it's face-centered cubic versus if it's body-centered cubic, we're going to do two calculations here. Now notice I gave you radius. All right, the problem says with an atomic radius. We have to have edge length to do these problems. All right, so you need to convert your radius into an edge length and then convert that edge length into centimeters, right? And that's what you would cube to get the volume of the cell. Mass of the atom, that's just multiplying, that's just dividing molar mass by Avogadro's number, and then multiplying by 4 because it's face-centered cubic. So the density you'd come up with if it's face-centered cubic is 1.539. If it's body-centered cubic, to turn radius into edge length, that involves a different calculation, right? But you still would get an answer in centimeters, which you would then cube to get volume of the cell. Mass of the atom hasn't changed, but what you multiply by does change, right? Because mass of the atom is still molar mass over Avogadro's number. So mass of an atom doesn't change. But what's different is I'm multiplying by 2, because if it's body-centered cubic, I multiply by 2. And the density you come up with, if it's body-centered cubic, is 11.3. Now the known value is 1.5, so whoever posted that it's face-centered cubic was correct. Does everyone see how we would do a problem like this if you were asked it on homework or a test or a quiz or something like that? Right, you have to calculate it both ways and then compare it to the known value. So here's the last type of problem we're going to cover today. Remember I said there are 3 types. The last type is using density to find molar mass. So this time I give you the density, and I'd have to give you what cell type it is too. And then you would figure out the molar mass, which you can then obviously compare to the periodic table. If it's not a real element though, then you're just working it out. So you're going to find volume of the cell, which you still know how to do, right? That's still edge length cubed. And then you're going to get mass of the cell, right? That's volume times density, because I'd have to give you density in order to do this. Now, in the previous problem, we multiply by the number of atoms in the cell. This time, we're going to divide. Why? Because we're getting the mass of the cell here. Okay? Volume times density gives us mass of the cell, but we want mass of an individual atom. Okay? And now, if we know that mass of an atom is equal to molar mass over Avogadro's number, this gets plugged in here. This is a constant, and then we can solve for molar mass. So let me go through one like this, and then I've got enough time for you to try one too. It'll just work out perfectly. So you're given a solid bar of an unknown metal. You determine the density of that unknown metal to be 11.5 grams per milliliter. And then, because you've got all the time in the world, you go do X-ray diffraction on it, and you figure out that the edge length is 4.06 times 10 to the negative 10th meters, and that it's face-centered cubic. So, what's the molar mass? And then based on that molar mass, you can determine its identity. So that's what we're going to do. So, let's list all our information. Oops, forgot to put in a blank. There we go. Okay, so what were we given? The problem tells us it's face-centered cubic. It's got an edge length of 4.06 times 10 to the negative 10th meters. And it's got a density of 11.5 grams per mil. And you want to know molar mass and identity. Okay, so the first thing we want to do, my eraser didn't erase very well, did it? First thing we want to do is we want to find V cell. How do you get volume of a cell? So that's edge length cubed, right? Now we're going to use meters. We want to convert that to centimeters, right? So we would say 4.06 times 10 to the negative 10th meters. There are 100 centimeters per meter, right? And so that's 4.06 times 10 to the negative 8 centimeters. And so that means A cubed would be 4.06 times 10 to the negative 8 centimeters cubed. So when I cube that, I get 6.692 times 10 to the negative 23rd centimeters cubed. Now we want to find mass of the cell. So how do we get mass of the cell? Well, we just found volume times density, right? So that answer that we just got, 6.692 times 10 to the negative 23rd centimeters cubed times the density, which is 11.5 grams per centimeter cubed. That gives me the mass of the entire cell, which is 7.696 times 10 to the negative 22nd grams. But I don't want mass of the cell, I want mass of the atom. Why do I want mass of the atom? Because ultimately, molar mass over Avogadro's number is equal to mass of an atom. If I know this and I know this, I can solve for this. Okay, that's why we're going to find mass of an atom. So how do I turn mass of the cell into mass of an atom? So you take mass of the cell, and we're going to divide it by the number of atoms in the cell, right? So this would be this value, 7.696 times 10 to the negative 22nd grams. And this is face-centered cubic. So what are we dividing by? 1, 2, or 4? Dividing it by 4, right? Because 4 of these fit into one of those. So when you divide it by 4, the mass of an atom is 1.924 times 10 to the negative 22nd grams. So now we can find molar mass, right? If molar mass over Avogadro's number is mass of an atom, I just plug this in here. Avogadro's number is a constant, right? So M of atom is equal to molar mass over Avogadro's number. So now, how do I get molar mass by itself? Molar mass would just be M atom times Avogadro's number. And so I got 115.9 grams per mole. And now I look at the periodic table. Which element has a molar mass of 115? It's most likely 10. Do we see how we did that one? All right, I've got one for you to try. We've got 10 more minutes, so that's perfect. So you try this one, then we'll go over it. An unknown metal crystallizes as body-centered cubic. You determine its density to be 10.8 grams per mils, and the radius is 136 picometers. What's the identity of this metal? All right, last one. Let's go through this. So we're told it's body-centered cubic. We determine its density, and we know that it's got a radius of 136 picometers. So we want to know the identity of this metal. So let's list our information. We know it's BCC. We know that its density is 10.28 grams per mil. And we know the radius is 136 picometers. Now, is radius going to help me in my calculations? Is radius going to be helpful for me in terms of figuring out the identity here? You need to convert it to what? Edge length, right. So in body-centered cubic, A is equal to 4R over the square root of 3. So that's 544 divided by the square root of 3, which I got 314.08 picometers, right? Because that's picometers. And now we want to convert that to what unit? Centimeters, right? How many picometers are in a meter? 10 to the 12 picometers per meter. And then how many centimeters are in a meter? 100 centimeters per meter. So that gives me 3.14 times 10 to the negative 8 centimeters. All right, let's get B cell. B cell is just A cubed. So that's 3.14 times 10 to the negative 8 centimeters. I want to cube that. So I got 3.096 times 10 to the negative 23rd centimeters cubed. Now we want mass of the cell, which is calculated by what? How do we get mass of the cell? Density times volume of the cell, right? So that was given in the problem, 10.28 grams per mil times 3.096 times 10 to the negative 23rd mils. Milliliters cancels. That gives me a unit of grams. So I got 3.18 times 10 to the negative 22nd grams. Now that's the mass of an entire cell. I want the mass of an atom. How am I going to get the mass of an atom here? Divide this by what? 2. Why are you dividing it by 2? Because it's body center cubic. So times 10 to the negative 22nd grams divided by 2. We're using 2 because it's BCC. So I got 1.59 times 10 to the negative 22nd grams. And now, if mass of an atom is equal to molar mass over Avogadro's number, you can just plug in and rearrange, right? 1.59 times 10 to the negative 22nd is equal to molar mass over 6.022 times 10 to the 23rd. And so I got 95.83 grams per mole. What element does that equate to? Molybdenum, right. How do we feel about doing these? All right, we'll be doing enrichment on it on Friday if you still have questions. Of course, you can also come talk to me between now and then. Have a good day, and I'll see you tomorrow.